chairs? Enough chairs? No? Okay, good morning, everyone. Crystal? Young? Sion? Angelia? Tober? Wind? Perry? Harrison? Lucian? Logan? Gary? Gary? Ray? Eric? Olivia? Curry? Jason? Aaron Gigan? Kratos? Romeo? Yuri? Yuri? Johnny? Johnny? Andy? Andy? Pray? Leon? Sinon? Oh, you are Leon? Leon? No? Sinon? Is he? Jason? Terry? Link? Oh, both of you are Link? Marvin? Peter? Pauline? Willow? Cindy? Penny? Theo? Liu Wang? Murphy? Sigler? Carvin? Carl? Tolman Lee? Henry? Zach? Cornell? Lucas? Andy? Bob? Bob? Scott? Ken? Anthony? Maxwell? Charles? Phoenix? Harry? June? And David. Okay, so let's start where we left last class. Only one screen is working, so the rest of these are not working. So, and it's small screen, so I think there is only one software next class, so we don't have four folks. So just let's spend these 2 hours in the middle screen. Okay. Okay. So we talked about energy signal, right, last class, and now we were talking about the power signal. Well, if a signal is not energy signal, it may be a power signal, right? It may be. Not saying for sure it will be. It may be a power signal. So let's find out that. So we know what is the definition of a power, right? What is the definition of a power signal? So here is the definition. Defined as the power dissipated by a 1 ohm resistor. Power dissipated by a 1 ohm resistor when voltage is applied across that 1 ohm resistor, right? Power dissipated in that 1 ohm resistor. How do you calculate? Well, we have already done it in signal system, so that's how you calculate the power. This is the general. If a signal is a periodic signal, then the definition is, right? This is the definition if the signal is periodic, right? 1 over T-O, and this limit from minus T-O, plus T-O, right? This is the definition for the periodic signal power. So let's move further. Here is the example. Want to calculate the power of this signal, right? So, well, you apply here, right? You apply trigonometric identity on this, right? Trigonometric identity, right? You do that, you solve it, right? This term is 0. You calculate this term is 0. So the power of this signal is a square divided by 2. That is the power of this signal, right? Now, now let's say a signal is not a power signal. It is not an energy signal, right? Now we say it's neither. Neither, right? A signal is not a power signal. It's not an energy signal. It's neither. So what signal comes to your mind? Neither. It's not a power. It's not an energy signal. What signal can be neither? Yeah. So what signal can be a neither signal? What should I write here? X of t. Neither. It's not a power signal. It's not a energy signal. Is this signal neither? RT. Is it neither? RT is what? RAM signal, right? So it's a RAM signal. Here, this is my RT, right? It's neither, right? Yeah, so it's neither. What about some other signal? What about some other signal? Okay. Is this neither? Because this is 1 and this is second. E raised to the power AT where A is greater than 0. Is it power? Is it energy? No. So both are neither, right? These are example of neither. Both are example of neither. Right. So a signal may not be a power, it may not be energy. So we call it neither. Right? A signal may be energy signal, it may be power signal. If they are not both, then it's neither, right? And at one time, a signal cannot be power and energy, right? It cannot be energy signal at simultaneously, right? Simultaneously, a signal cannot be power and energy signal. It has to be an energy signal or it has to be a power signal. But simultaneously together, you cannot say a signal is a power and energy both, right? No, it cannot be, right? Okay. Okay, so let's move further. Logarithmic power calculation, right? We will be talking in communication system. We'll be talking about dB, right? dB. You know dB, right? So yeah. So dB. We will be working with dB, right? What is dB? How do you find it? You have power in watts, milliwatts. You convert it into dB. How do you convert that, right? This is the formula to convert. We are using logarithmic scale now, right? So here is how we find power in dB. And we'll be talking about dB a lot, right, in this course. Here, P, where P is power level in milliwatt. That's 1 milliwatt is 0 dB. 1 milliwatt is 0. What about 100 milliwatt? That is equal to 20 dB, right? Yeah, 20 dB. Now, okay, actual signal is in watts, right? I am in dB, I work on that, and then I have to convert back into milliwatts, right? So that's how you convert in milliwatt. Now, a signal is back in milliwatt. Power, not signal, power is in milliwatt. So we convert milliwatts, we convert it into dB, we are done. Then we bring back into milliwatts, right? So that's how you convert it into milliwatts. Okay. So the power level at any point in a transmission link can now be calculated by adding the algebraic sum of gains in dB up to that point to the input level in dB. What does that mean? Let's see through an example. What does this sentence mean, right? Okay, so here we are. We have an example. Here we have this laser, a semiconductor laser couples 5 milliwatts into an optical fiber link. This is a digital communication system, right? Here we are sending some data. Digital communication, we talked about 0101, right? Binary number. We are sending that data through this laser transmission link, right? This is my input. Here, P1 is my input. And P1 is 5 milliwatts, right? And these are when you are sending data, you have cables, you have connectors, you have splitters, right? Cable, well, transmission medium. Here is my transmitter, here is my transmitter, here is my receiver. In between, there is something, right? We have cables, we have connectors. So these are those cables, connectors, right? And splitters. And they are taking this much power. Now look at the question, right? Here I have 5 milliwatts entering into my transmission system, right? Transmission system, what? The wire or the wireless, whatever you call, right? Transmission medium, channel. So here, those components, let's say this is cable, it is taking minus 11 dB, and let's say I have a connector which is taking minus 6 dB, and then I have a splitter which is taking minus 3. At the end, when I reach at the receiver side, I need to calculate how much power is there. P2, which is at the receiver side, right? See, optical receiver, RX receiver. So I want to calculate how much power is there at the receiver. If I am sending 5 milliwatt I am sending, or is utilized by the system, how much power I would have at the receiver side. And here is the problem. The problem is I have here dB. Here I have milliwatt. So the first thing I need to do is convert this P1 into milliwatt. In dB, right? Or dBm. So here I have 5 milliwatt. Here I have 5. Here I have dB. So first thing is convert that into dBm. So that's how we convert, right? Using the law. So 5 milliwatt converted into dBm. Now here, if you look at this, I have all minuses, right? So algebraic, I have to add them algebraically. So here I am adding algebraically. If I add that, right? If I add that, I got minus 20, right? So here, if you go back, here I have, up till here I have minus 20, right? So now, and here I have plus 7, right? How much power I would have here? Algebraic sum, right? So 7 minus 20. So that would be minus 13 dB, right? Now I need to convert it into milliwatts. I know the formula. Just plug in the formula, you will get the power in milliwatts. Right? Make sense? So here, what I want to do, I want to calculate this P2, right? Compute the power input to the optical receiver. Some power is taken here, some power is taken here, some power is taken here. I want to calculate how much power is here, P2. So I have P1 in milliwatts, so I have to convert it into dB because all of those are dBs, right? So just add them algebraically. Add them, right? This power would be sum of this power plus sum of this plus this plus this, right? Since they are negative, so I'm getting a negative number. So that's why I got a negative number here, minus 13 dB. Now, if I convert it into milliwatts, well, it is 50, right? Okay. So we'll be dealing in dB in this course. Now, Now, some basic operation on signal. Well, time reversal, right? X of t, X of minus t. Signal, flip. A signal, flip it. That is minus, right? Minus t. Similarly, time shifting, right? If I am advancing the signal, if I am delaying the signal, here I am delaying the signal, right? Plus, if minus. If I put it plus, if I put a sign plus, I'm advancing the signal, right? So delay the signal, advance the signal, right? Time shifting, and then time scaling, right? Time scaling. So here I'm time scaling a signal x of alpha t, where a or alpha is constant. So I'm scaling the signal, right? So let's say I'm scaling the signal. I have a signal. Here is the alpha t, right? Where alpha is some constant. Now I have two conditions. One is, let's say alpha is equal to 2, and one is alpha is equal to half. Here, if I put alpha is equal to 2, what I'm doing, and here if I put alpha is equal to half, what I'm doing. If alpha is equal to 2, what I'm doing with the signal? Yes, I am compressing the signal. So here, compression, right? And here I am expanding the signal, right? Yes. So I'm compressing the signal, or I am expanding the signal. See here, if alpha is greater than 1, this signal is compressed. If alpha is less than 1, then the signal is expanded. So here are some examples. Here I have a original signal, flipped version, time reversal version. So this is the flipped version of that signal, and then delay. So here is the delay, right? I'm delaying by 2, and then I am, in this here, see, I am advancing the signal by 2. Here I am compressing the signal, right? 2t, and then here I'm expanding the signal. So these are a few examples. Now, amplitude scaling. Here is the amplitude scaling, right? X of t. So I'm amplifying a signal. So here, this shows amplification if a is greater than 1, right? So I'm amplifying the signal. Similarly, what is B? Well, B is the DC level, right? B is the DC level. B shifts the DC level of this signal. Well, plot the following signal. Well, we've done a lot of plotting in previous courses, right? Well, don't expect any question on plotting in this course. Just maybe in homework you would have plotting, but in the exam, I'm not expecting any question on plotting, right? So anyhow, if I want to plot those signals, so here are the plots. But you don't need to work on this for your exam. Plotting is you already done a lot of plotting in signal and system 1. So these are here, right? So you're plotting those signals. Now we talked about systems, right? System. So what is a system? System. What is a system? You have a black box. This is input, and this is your output, right? This is a black box. Black box. What is a system? From your signal and system 1, system is what, right? So this is a black box, right? So what happening if an input into another signal, right? That transformed version is my output. So for example, if I want to put here, uh, if I want to put here a squarer, or let's say I put a here integrator, right? My signal x of t may be something, some x, whatever, right? This will work, this black box which is now integrated, it will give me an output which will be integrated, right? Integration of x of t. Let's say I want it square law device, right? I say it's a square law device. Square law device. So this is now, it will square my input, right? So it will give me x square of t. Here it was x of t. So it transformed, right? It transformed the input, and it is giving me something, a new signal. It is giving me a new signal. This called system, right? System works on input. It transforms that input and gives you another signal. That another signal is called, that transformation is called system, right? System. So here, right, we are talking, okay, so we are talking about here the continuous time. Same applies to discrete time, right? Same definition applies to discrete time. In the communication system, a system entity may represent the effect of transmission media or signal processing operation on a signal. What does it mean? Here, what it means. An example is the attenuation in distortion of the output signal produced by twisted copper wire here. I have a sender, I have a receiver, right? Transmission. There is this channel, right? Let's say that channel is copper wire, right? Physical wire. So when I'm sending a signal, noise will add, right? I have a pure signal, let's say speech signal, and I'm sending, well, noise will add, right? That at the output of the channel, right, what I'm getting? I'm getting a distorted signal, right? I'm getting a distorted signal. Like for example here, this is my speech signal, let's say, right? Here is my channel, which is a twisted wire, right? So what do you think I should get? I should get this signal, right? I should get this signal. But here, noise is added, right? So what I'm getting here, I'm getting something like this. So it's a new signal now, right? It's a new signal now. So this can be a system. Another example, filter, right? How do you make an analog filter? How do you make an analog filter? Yes, capacitor and resistance, right? Depending on what kind of filter you want. So you can remove that noise by using the filters, right? Like for example, and the high frequency, right? Here, on the received signal with the intent to remove out of band noise. Here, another example modeled by a system entity is the filtering action produced by interconnection of circuit elements. What are circuit elements? Resistor, capacitor, low pass filter, right? You have produced, well, you have designed a low pass filter. You want to just, okay, how much is my speed signal maximum? 3.4 kilo, right? So you design a filter with the cutoff frequency max is 3.4 kilohertz. That's it, right? Whatever extra frequency is, it will get removed. Right? So you can say a filtering is, or filter is also a system, right? Block diagram. Well, this is the block diagram of a system, right? We have an input signal that will work on that. The system will work on that input signal. It will transform, right? We just saw it transform the signal. You get another signal by 2. That is basically the output. square law. It's a system, right? Square law device is a simple example of a continuous time system, right? So input is x of t, the device, the system, it's a square, it will square that, so output is by 2. So now, see, the signal is transformed, different. Signal was x of t. The system made it x squared, right? The system made it x squared. It states that output signal value at time t is equal to the square of the input signal value at that same time, right? So just this is square now, right? Output I'm getting x squared, which is different than x of t, right? So that's what the system is doing. It is transforming, it is changing. Another example would be delay. It's also a system, right? I have an input x of t. I want to delay it by some t o. So I design my system. Okay, it's a delay now. Delay the signal by t o. So here it is delay. And then accumulator, right? What is an accumulator? Here is the accumulator, right? You know, discrete. So I can write this equation in this form. I can further write in this form. So what is this? This is basically the previous, right, output plus the current input. That is what a accumulator is, right? The output at time instant n is the sum of the current input plus the previous outputs, right? But I can write this equation, right? Well, first of all, this equation into this, right? And then I know what is this. This is basically y of n minus 1. This equation, right? This is y of n, then this equation is y of n minus 1. That means my current output is sum of the previous outputs plus the current input. That is what the accumulator is, right? This is accumulator. Similarly, if I want y n minus 1 here, I want y n minus 1 here. So it will be the previous, right? The previous input plus the, see here, is the sum of all previous input sample values from minus infinity to n minus 1, and then go back, y of n minus 2, y of n minus 3. So you are going back each step, right? You are going back. The system accumulates, cumulatively adds, that is, it accumulate all sample values. Accumulation means what? Adding, right? Adding. So this is accumulator. And this is also a system, right? Now, linear system, right? What is a linear system? Here, the system is linear, right? If x of n results in the output y1, and x2 results in the output y2. So if I say a system is linear, it has to follow, as you are seeing in this example. What are you seeing here? It has to follow what? What is happening in this? It says x1 results in y1 and x2 results in y2, and it has to result in this way. What you are seeing here, you are seeing what? Two conditions, right? One is they are adding, right? So additivity. Right? What about the second one? Scaling. Scaling, right? Scaling, or it's called homogeneity. Right? Homogeneity. I don't know spell it. E-I-T-Y or I-E-T-Y or anyhow. It's scaling, right? So here, scaling is there. Alpha, x, alpha, y1, right? Beta, x2, beta, y2, and plus additivity. So both properties has to be satisfied in order for a system to be linear, right? If any one fails, then the system is not linear. System is not linear, right? So this is what a system, a linear system would be. It has to follow additivity and the scaling property. Both have to be well, for discrete, what we are just replacing it by n, right? So same definition applies for discrete. Both has to follow for discrete as well. It has to follow. And a system which does not, well, we just talked about that. If it's even failing one of this, it is non-linear, right? Let's see an example here. Okay, now, is this linear or is this non-linear? The integrator. What do you think? Is integrator linear or non-linear? For linear, it has to follow these two tests, right? It has to follow these two tests. So just perform those tests and see is it linear or not. Do both tests. I mean, you don't need to solve it. You can tell right away. Scale it, and then do the additivity property. Right? Is it linear? Yes, it is linear, right? Yeah. So here, both tests are performed, right? Additivity test is performed, and the scaling is performed. Alpha is scaling, and this is additivity. So yes, it is linear. What about square law device? X square t. Yeah, it is not linear, right? So let's see that example. Yeah, here this extra term will make it non-linear, right? Square law device, it's non-linear, right? When you apply both tests, you will see here this term will make it non-linear. What about accumulator? Accumulator. Is it linear or is it non-linear? Accumulator. Linear? Yeah. Apply both tests. Yeah. So if you apply both tests, yeah, it is it is linear. Yes, it is linear, right? Apply both tests. Now, memoryless system, right? System with memory and system without memory. So a memoryless system is one whose current value of the output depends only on the current value of the input. Current value of the output depends only on the current value of input. That is called a memoryless system, right? So, integrator. Is it a memoryless system or does it have a memory? So the definition of a memoryless system is the current input depends on the current output depends on the current input, right? That is a memoryless system. So if I have an integrator here, is it memoryless or it has memory? Or why? The previous time, right? Minus infinity up to some certain time t. So yeah, it has a memory. Okay. In your circuit, you have elements, right? Elements. Which of them is memoryless? Which of them has memory? Resistor R has memoryless, right? Yes. Memoryless. What about capacitor? Has? Yes, capacitor has memory, right? Capacitor has memory. What about square law device? X square of t. Y of t is equal to x square of t. Does it have memory? Square law. Y of t is equal to x square of t. Is a square law device, right? Does it have memory? No, right? Yeah, it's a memoryless. Is it memoryless? Yeah, okay. Now, time invariant system. What is it? Okay, what is a time invariant system? Time invariant system is what? if you introduce a delay in the input, the same delay should be in the output, should be reflected in the output, right? So if I am introducing a delay in my input here, the output should also have that delay. This is called time invariant system, right? Time invariant system. Similarly, for discrete, we call it shift invariant. In continuous time, we call it time invariant. In discrete, we call it shift invariant. Shift invariant system, right? Definition, same definition, right? Whatever delay I am introducing in my input, if that same is reflected in my output, we call it time invariant system or shift invariant system. Let's see some example. Okay, now, okay. Where integrator, is it time invariant system or is it time varying system? Integrator. So you have to apply this definition, right? So just think of that. You have XFT, which is this integrator. You are applying this. You are introducing a delay. That delay should be reflected in the output as well. So if you have an integrator, what do you think? Integrator. It's not time invariant. Is it time? Okay. Time invariant and time variant, two things, right? One is time invariant, one is time variant. So is it time invariant or time variant? Sure? Sure. Okay, let's see. Yeah, this one. No, this is time invariant system, right? Just into the delay, right? You will get the same delay in your output, right? So this is time invariant system. On the other hand, if okay, this one, this one, we have. We'll be talking about this in chapter 4. Let's say we have a signal XFT. This is called modulator. And we'll be talking about amplitude modulators or frequency modulators in chapter 4. But just for you know, this is a signal. It's a very speed signal. Is how much frequency? 3.4 kilo, right? Max 3.4 kilo. And here I have this fast range. Remember we talked about that. It has a very high frequency. This FC is a very high. Let's say mega, right? So if I multiply this signal with this, I will get some output, and that output is this, right? Now I apply this time variant, time invariant test. If I do that, you can see there is a difference, right? There is a difference. So this one is basically time. If I introduce a delay, then this amplitude modulator is a time varying system. Time varying system, right? What about accumulator? Is it time variant, shift invariant, or shift varying system? Accumulator. So that means if I introduce a delay, that delay in this accumulator output should also be reflected. So is it shift variant or is it shift invariant? Yes, shift invariant. Yes. See here, the same. Oh, sorry, this is the moving average, right? It's not the move. You have done moving average in your signal and system too, right? Yeah. So this is the moving average. If you introduce a delay in the moving average, you will see it's a shift invariant. Okay. Then LTI system, right? Now we have linear, we have time invariant. Together we call it is an LTI system, right? LTI system. And we will be in this book, in this course, we will be talking about the LTI system, right? We'll be talking about the LTI system. So here, if you remember, in your signal and systems one, you have an here is my input x of t. If I say this is an LTI system, right? Then that means it has h of t inside. Here I am getting x of t convolution with h of t. That is the output of an LTI system. Now the question is, what is this h of t of an LTI system? What does it mean, h of t? What is that? What is it doing? H of t. It is what? It is the h of t is what? Here. What? H of t of an LTI system. It is the impulse response, right? Impulse. What do you mean by impulse response? LTI system. Right? Now, what is impulse response? How do we define impulse response? When x of t delta t. When x of t is delta t, my system will respond, right? The LTI system will respond. That response is called the impulse response. Why? Because this is impulse, right? My input is impulse. So now I need to solve this now, right? Here the impulse response is h of t. It will give me some output. That output is the convolution of a signal with the impulse response of the system, right? We solve this by what? We solve this by using the integration minus infinity to infinity x of tau, x of tau h of t minus tau beta. That's how we solve, right? Where is this integration coming from? How do you do that? And same definition for discrete, we'll write down n, right? In front, we won't be doing that. See here? So here we are doing that. Right? Where is this integration coming from? This is called convolution. What is convolution? Right? This is convolution, right? What is convolution? What is happening? What is happening here? Let's say let's say I have this signal, right? Let's say this is x of t, and then I have another signal which is this, and this is h of t. This is the impulse response. I want to convolve both, right? This thing. How do you do that, right? You flip that here, and then you move it, right? So for example, here there is no convolution. So you move it further, right? You slide one signal. This is your choice. You can slide x or you can slide h, right? So you slide this signal. Let's say the signal now is somewhere here, like this, right? And then you slide further and further and further. So what you are doing, you are measuring this area, right? You are finding this area. How do you find the area? Indeed? Yes, that's why this integration is coming. You are finding the common area, right? You are finding the common. How do you find in continuous time? How do you find the common area? What is integration, right? Area under the curve, right? Depending on where I am, it is 1 or 2 or 3, whatever, right? T would be whatever. So I'm finding the common area. That's why the integration is coming. That's why the integration is coming from. So that's what convolution is, right? That's what I'm finding the common area between the two, right? So one is the system, one is the impulse response of the Did I miss any attendance? Scott, yours? That you were in 4 or 5? Oh, sorry.